Yes, sir.
Yeah. Okay. Remember that in the previous, okay, good afternoon. Remember in the previous class, in previous lecture, we talked about the sedimentation tank, and as a review, this is the treatment plant's process. It will start from the intake, and was the intake. And we have in the intake a concrete tank, or usually it will be concrete, it's called sump. And these sumps will have a length, width, and depth. And the basic idea that we should take care about how to design this one by the Q maximum monthly or Q minimum, which is the zero point 0.7 of the maximum monthly, and 1.4. And from these two ones, we can find the volume by having maximum volume of a volume of two equations. You remember that we have 2 minutes, we have 5 minutes, and so on. After that, we found the horsepowers of the number of, it means the number of the pumps and the horsepower for each pumps. And there will be the first unit, which is the we'll go with the pipes to this unit, and then from this unit we have the clarifiers, which is usually will be circular shape. And circular shape, what I mean by the circular shape, it means that this is the top view of the tank. Again, I'm sorry for the disaster that we have in drawing. Maybe I can use another thing. Yeah, draw. Yeah, okay. Okay, will be the top view of the tank. So what we have here, usually the main, um, there will be a tank here, and we have to draw. There is a pipe, and with this pipe is coming into this one. So this is the first unit, and the water is coming from the raw water is coming from the intake and the sum, and it will be collected here, and it will be, this is called distribution chamber. It will be have more than one we have more than one more than one clarifier. It will be more than one. So what will be done? The water is coming through the distribution tank to two tanks. Now, if I have here Q, so this is will take half of the Q, and this is will be half of the Q. And from the design, we say that the number of these clarifiers, and by the way, the clarifier, this is the top view of the clarifiers. If you wanna see the whole clarifier shape, it will be like this. This is the top part of the clarifier. By the way, what is the mechanism of the working of this one? The water is coming from bottom. Some of the tanks, we have the water will come from the bottom, and it will be upward. Some of the tanks, we have the water is coming to this chamber. This is called inlet zone. Excuse me, just I'm sorry. So some of the tanks have the inlet zone. This is will be the inlet zone, this part. So the water coming in a pipe and it will be here and it will go down. And then this is the skimmer. This is called skimmer. And after that, the water when it will be collected in this tank for 8 hours, and then it will be overflow for this one. This is called weirs. And you can see the video. I think you can have just put a link. Here's the link. You can see how these tanks are working. And so the idea is to see how these tanks are working. Now back to this is for the circular shapes. So the top view of the tank will be look like this. So the water is coming here, and this will be uplift. So from if I want to check, let me say, if I want to, this is the cross-sectional view. So the water, the pipe, the inlet pipe is coming from bottom, and it will be, there is a wall inside this tank. So the water is coming inside and it will be distributed through the tank this way. And it will stay for a period of 8 hours or less. And then there will be, if we have particles in this tank, sands, any sands, it will be settled down till we will have all the settling here. It will be collected. Now, the top part, we have clear water, clear zone, or the clean water zone. It will be collected here. What I will do, I will have a channel. Will be a channel. The water is jump to this channel. They are collected here, and then after this is a circular shape, then I will have a pipe will send the clean water to the filters. So the procedure is that the water is coming this way, inlet, and the inlet is having a sediment particle inside this, and it will be collected. This is called inlet zone, and this is settling zone. This is settling zone. And it will be settled all the particles here. Then there is a clean zone. What is the clean zone? That the water will be cleaned here, and then it will jump over a weir. This is called weirs. And then after that, the whole weir are connected as a circular shape. There will be a pipe here, and this is called to the effluent. Effluent. So we have influent or influent, and there is an effluent. So what is the influent? The influent is the raw water that's coming from the land. It's holding raw water, which is holding particles, solid particle, and the clean water or the filter, it's called clean water. And when I talked about the clean, I'm saying usually there will be a clean water, or if the water is very dirty, so we may have another part treatment before the use. So, but this is the usually what we have in the sedimentation tank. So this is the procedure of the working. Now, we see there is definitions for what we have in this tanks. You can see will be the top view of the tank, right? So the diameter of this tank, was the diameter of the tank. So pi d square over 4 is the area, the surface area of this tank. This is in case that we have a circular shape. So we have the surface diameter pi d square over 4. And now we have SOR. What is this SOR? The SOR, the definition of SOR is called the surface over flow rate. Surface over flow rate. What is the surface overflow rate? Can you answer? What I mean by the surface overflow rate? We have Barham, Maryam, Mijda. The only
I
four.
believe
Yes.
it's the
Yes,
the
Maryam.
area at which the water flows in, like speed
Exactly.
that it flows in. I'm not
Yeah.
sure if this is correct, but
Yeah, the top area or the bottom area. It means the top surface area of the soil. If I have this area and if I have the Q is the flow that will go inside this tank. So dividing the Q by the area AS, this is this AS, so it can give you a SOR. So SOR, the definition of SOR is Q divided by area. By the way, SOR is velocity because it's the unit of meter cube per day divided by meter square, which give you a meter per day, which is the units of the velocity. So SOR is the surface overflow rate. That's the Q divided by the surface area. It means the top area of this tank. And we need this SOR to be set for 2280 meter per day. This is the standard number for design. We use this for design. What I mean by the design, it means you have the Q, you want to see how much is the area of this, the diameter of the tank that I have. This is in case that we have a circular shape. While if I have rectangular shape, so what will be happen? So for rectangular shape like this, there is an L length, there is a width. So there will be will be the water is coming in this way. Sorry. If we have a tank like this, so the water is coming inside this, and it will come inside this tank. This is called inlet zone. And this is the length of the tank. And there is a width of the tank. And there is a height of this tank. So now what is the surface area? AS is equal to length multiplying by W, right? So this way SOR is equal to the Q divided by this surface area, which is equal to Q divided by L times W. Also, this is the same definition. The same definition means the SOR. Clear?
yes, sir.
Now, yeah, this is the SOR. We have done with the SOR. We have another velocity, which is the horizontal velocity. So this is the SOR, and some of them are saying this is the settling velocity. It's the when we have a particle, it tends to be settled. So any particle in this time is going to settle. It will find itself down. So we have, it will be by the effect of gravity. So this is the Vs, and there will be a V horizontal. The horizontal velocity means V horizontal will be the same Q divided by this area. This is called cross-sectional area. Cross-section means the area that will be perpendicular to the direction of the flow. So perpendicular area to the direction of the flow in this case is H times W, right? So Q divided by H times W, it's giving you a horizontal velocity. So, and this is if you have a rectangular shape. And this, if I have a circular shape, so what's gonna be the horizontal flow in this case? Mr. I have a tank, and this is the cross-sectional. What will be the horizontal velocity?
Sorry, doctor, I don't understand your question.
Okay. Yeah, we have a tank like this. Okay. The water is coming from the bottom until we have area like this, and then the water is coming down from this inlet. Now, we said that if there is a particle, this particle is going to settle down. It will stay here. Will be the direction of the movement of this particle, right? So this particle will settle by the effect of the gravity, so it has a settling velocity like this. And also it has a horizontal velocity VH. Now, if we have the diameter of this tank here is D, right? So we have the Q. So Q divided by D squared over 4, we know that this is the SOR, right? So the SOR, it's called surface area. But the cross-sectional area will be what? The area that will be perpendicular to the direction of the flow, which is the circumference of this type. Look at this one. This area is called AC, cross-sectional area, which is the cylindrical surface area. So the V horizontal, it will be equal to Q divided by A sub C. V horizontal is equal to Q. What is the surface area of this cylinder part? It's equal to, this is the edge. So the circumference of the circular shape is pi d. So pi d multiplied by h. This will come and give you a cross-sectional area. The direction of this flow perpendicular to what we have. Okay, now I want to tell you. You can see this shape. So if this is the tank, this area, this is the circumference of the times the edge. The water is coming from here and it will go this way. So the direction of the flow will be perpendicular to this shape. This is the surface area of this cylindrical part. We'll call the cross-sectional area. Now Q divided by this cross-sectional area is giving you horizontal flow or horizontal velocity. Now, so SR is equal to Q pi d squared over 4. This is for pi d. Pi d is the circumference times the h. Is it now clear, Mijda?
Yes, doctor. But if we have to know the area of the cylinder, we have to sum two things. First, the area of the circle, and then the.
Absolutely. I mean, when I mean surface area, I mean by the outer part.
The outer part. Okay.
The outer part, not the top part, not the bottom one, just only when we have a perpendicular area to the direction of the flow. The direction of the flow will be radial, right?
Yes.
This will be radial, right? So you have this pi d is the circumference of this tank. So pi d times the h will give you the surface area, which is called the cross-sectional area. The cross-sectional area, the area that's perpendicular to the flow. So the Q divided by this one, it will give you the horizontal velocity.
Yes.
Okay?
Yes, doctor. Thanks.
So now we have those two main points. Back to what we need. This SOR we talk about, this is a settling velocity. And by the way, assume that we have will be, for example, if I have different shapes, was a solid particles. This solid particles, this is a sample of raw water. Okay, so this sample of water will go inside this tank and will be settled. So we have greater part, we have very small part, and we have in the middle. So each of them having their own diameter, right? Now, there are some of the particles exactly having the velocity. Their velocity will equal to the Vs naught, the Vs, SOR. So some of the particle, by the way, the velocity of the particle, any particle can be settled, any particle, if you have any particle, any solid materials of this diameter, and it will has a horizontal velocity. So Vt is the terminal velocity or the settling velocity of this particle will equal 1 over 18 g over mu rho particle minus rho water d particle square. So any particle can be settled with a velocity of this is called Stokes law. Now, what we have in Stokes say if you have any particle diameter, you can have a settling velocity like this. Now, we know that G is meter per second square divided by mu can be measured as a kilogram per meter per second, and rho can be kilogram per meter cube, and the particle will be in meter square. So we can say will be meter, and the 1 meter will be 1 meter, and the kilogram will kilogram. So there will be a second, they're second with the second. So the units of this velocity will be meter per second. So it's okay. Now, the theory is that we have a particle can have a settling velocity like this, and we have SOR, which is nominated for a velocity. So usually those particles, if they were equal, what I mean by the equal, if this Q, the SOR area of cross surface area, which is means by SOR, if SOR was equal to 1 over 18 G over mu rho particle minus d part rho water d particle square. So definitely this particle is called dp 100%. What I mean by dp 100% or d, this means that those particles will be removed 100%. Means that, for example, if I have 5 millimeter, 10 millimeters, and it was 20 millimeters and 25 millimeters. If after my calculation I found the SOR was equal to that settling velocity, so from these ones I can find d particle. For example, if the d particle was a d 10 millimeter, what I mean by this, it means every particle having a diameter of 10 millimeter and more, there will be a removal 100% of this particle shape. Usually, when we have 10 millimeter for this case, for this example, if 10 millimeter was the diameter that's it will make the SOR equal to vessel length, means they have a settling velocity. The settling velocity will equal the SOR, and both of them means that it will be definitely settled. in case that we have more particles greater in shape, in size, more than that T 100%, it means that that also will be settled at 100% or 120 to 100%. So if D particle was equal to T particle 100%, or it's called dP naught, that means the the particle 100% be removed, and or any particles its diameter greater than dP naught or dP 100. So any particle more that its diameter was greater than dP or dP naught, so it's also removed 100%. Now, why we are talking about 100%? All the particles will not be removed. There will be a percentage of the particle will stay in the water because their sizes are very small. But those particles will be definitely removed when they have a specific diameter. This specific diameter will relate it on the dimension of the tank, on the Q. So if you can, if you want to make sure you want a very good design, you have to first check the solids that you have in the raw water. And then after that, based on that raw water, you will find the settling velocity for that particles. It's easy, just apply this equation. Then you will get the SR. The SR, the required SR, just to relate that particle to be removed. Now, you have the Q, the accounted Q, you have the flow that you have to send to the people. Now, what's left for you? I have this and I have that. So just we need to know how much is the cross-sectional area which is equal to pi d squared. Now, when this one are only diameters and stay unknown, you can find the required diameter for that tank to be capable for removing this particle size. This is the way that we are using it for design of such a tanks. Okay, is it clear for you?
Yes, sir.
Yeah, so you have to take care about first of all, you have to see, this is like you are a physician or you are a doctor. When you want to see, you want to make a treatment, you are going to design a structure. So first you have to see what you have, what the patient have, what the water inside the water is there. So you have to know, make a test for the particle included in this time, and based on that you have to decide. And later on, you have some other steps to check on your design. For example, after you make a design and after you did this one, you have to check after having this tank, what the waters will collect it here. Now, the clean water will be jumped over. There is this is called a trench or a weir. This is called weir. So weir, how much will be the depth of the weir and width of the weir? This is called weir loading. Weir loading is the Q divided by meter length of that weir. So weir loading is the Q that will be escaped from the tank of clean water Q divided by the circumference of this tank. So the circumference of this tank, I mean by the circumference, is the pi d. So Q over pi d is the called weir loading. Weir loading usually, this is will be meter cube per day, and this is will be meter, so usually it will be meter square per day. Now also we have specific standard numbers for the weir loading. So you have to check over weir loading, is it within the standards or not. Now what other things that we have? That's it, yeah. But in case that we don't have, for example, we said that we have the particles are small and greater. For example, if the d particles was 10, that means, what about the fall of the 5 millimeters diameters solids? Are they are not removed 100%? They are not removed 100%, but they also have a velocity which is smaller than the VS node, but still some of them will settle in another way, and we will find in a ratio. The ratio is, it will depend on the velocity. So if the particles of 10 millimeters are giving you a settling velocity, which means 100% will remove, then the Vs of the 100, and then we have to find in the same equation the settling velocity of those particles having diameter of 5. Then dividing that Vs by Vs naught or Vs 100, it will give you a ratio. This ratio will means, for example, it will be less than 1, for example, 60%, 70%. It means that all the particles of 5 millimeters they will not 100% will be settled, they will be 70% of them, they will settle. And now here's the sedimentation role, and here's the sedimentation idea that we are working on it. I think, yeah. I think we have some of the standards. Yeah, let's go to see this example. The question here is asking us to design a rectangular sedimentation tank to treat 4,750 meter cubic per day. Now look at the question. It said that the smallest particles that should be 100% removed is 0.303 millimeters. So that D particle is equal to 0.03 millimeter. This is the particle that should be 100% removed. What means it's dp naught or d 100%, or d particle naught or dp naught or d 100%. Some of them are named as dp 100%, dp naught. Now, what should we do? It asks us that it gives us that the Vs naught is the d particle should be removed 100%, 0.03. So what we need to know, and by the way, any particle smaller than this, it will be also definitely will be removed. So we have the Q, it's 4,715 meter cube per day, and we don't have area. So when it asks us to design a rectangular tank, it means it asks us to find its length, its width, and its height, right? And this is the length. So we need to know how much is the dimension of this one. So starting from this trick, or this given a very good information is given to me, that this will be the 100% particle removes. So when we are applying the settling velocity, it asks 1/18 g over mu rho particle minus rho d particle square. So I have this, and I have rho water, and I have this is also rho particle is equal to specific gravity times rho water, and I have G, I have mu. So what I will find the Vs, and because this is 100% will be removed, this is called Vs naught or SOR. So this is a key, because I have the Q and I will have the SOR. So from those two ones, I will get the area. Now let's check for this SOR. Now 1/18, G is 9.81 meter per second square. And what about the G over mu? Mu, where's the mu? The mu, here's the mu. The mu is 1.008 kilogram meter per second. So 1.008.7 and 10 to the power minus 3 kilogram meter second and times. What is the raw particle? The raw particle is specific gravity times raw water, and specific gravity of this particles are 1.65. By the way, means 1.65 means it's a sand. As you know, for sand we have 1.65, 1.66, and so on. So 1.65, this is the specific gravity of the particle times raw water. What is the raw water? It's 1000 kilogram per meter cube minus raw water, which is the 1000 kilogram per meter cube also. So times the d. Diameter of these particles that will be settled 100% is 0.003. Okay, and 0.003 millimeter. So it will be 0.03. This is millimeter, and I should convert it to make it in meters. So I will multiply it by 10 to the power. Hello, Mawar, how?
6,
Millimeters, 2 meter,
3, please.
3. So then this is going to be squared. So this is will be square. Now this is will be meter square, 1 meter cube. A meter cube, this meter with this meter, and this is will be meter, and the seconds, kilogram with the kilogram with the kilogram, and the second is 1 second. So the answer will become in meter per second. Am I right?
I am getting 6.32 times 10 or minus 4.
I'm sorry, just can you repeat that?
6.32.
6.32
32.
times
10 to power minus 4.
like this.
Yes.
Very good. So this is the velocity of the satellite. And what is that? It means that we have a particle like this. Its diameter is 0.03 millimeters, and it will have a settling velocity is equal to 632 times 10 to the power minus 4 meter per second. And this is will be this particle 100% will be removed. And this will be equal to SOR. Why? Because this definition from that one is those. We want to remove that one. Now, what is the Q? The Q is the Q of this tank. It will be 4,750 meter cube per day, right? 4,750 meter cube per day. Now, from the definitions, the SOR is equal to Q divided by area, surface area. Now, from this one, I can say the surface area of this tank is equal to Q over SOR. What is the 4,750 divided by the SOR, which is the 6.32 times 10 to the power minus 4 meter per second. Now this is meter cube per day. Now you have to be careful to convert this one. So per day means where is the day? I have a day 24 hours times 60 times 60. So this is second per day. Now this day with this day, and second with the second. Now it will become meter square. I'm sorry, this is to apply this one. Okay.
Dr. Akko,
But yes,
the value that I get from the VS is totally different from this value.
why?
Actually, I don't know. I repeated 100 times calculating, but it is different. I got 2.95 multiplied
I
to the
have maybe this point. Have you squared this point
yes,
43?
yes.
Let's let's check that one. So it's 0.03 square times 1000 times 0.65 times 9.81 divided by 18 divided by 1.0087. Yeah, I think we have 3. It's 0.31. I get 0.316 times 10 to the power minus 3 meter per second. Mirza, did you
Yes,
get?
doctor.
This is what the number I'm talking. Is that the true one?
This is the number that you get?
Yeah.
No, I got 2.95 multiplied by 10 to the power minus 4.
Like this?
Yes.
I don't
For the
know.
whole value, for the whole VS.
Yes, I'm talking on the whole.
I don't know why, but I just calculated many times.
So 1.65 minus 1 is 1.65 times 0.03 squaring times 1000 times 0.65 times
After yours is true.
yeah, thank you. Mine is true times divided by 1.0087. It's 0.31 times 10 to the power 33. I think mine is true. It's not 0.63. You may just not multiply this one squaring. So the answer was, here's the answer. 0.316 10 to the power minus 3. Okay. 0.316 times 10 to the power minus 3 meter per second. Now, as I told you that we have to divide this one. Second, we have to 24 per hour times 60 times 60 seconds. So this is what can be the second with the second. So the result will becomes 4,750 divided by 24 divided by 3,600 divided by 0.316 times 1,000. So I get the area is equal to 173.9 meters square. Means what? Means the area of this tank, this is the surface area of this tank, which means the length times W. So the length times W is equal to 174 meters square. And in the design, we have a ratio for L to W. You can see. You can see. Look at this, the rectangular shape. We have L, it should be less than 100 meter, that's one. And the length to width ratio is to be 2 to 1 or 5 to 1. So it will be between 2 to 1 and 5 to 1. Now, if I assume that, for example, I will use 2 to 1, it means the length will be twice the width. So what that means to me, or how can I, if this L equal to 2W means 2 to 1. So what will be here in the calculation? I will say, so the 174 meters square will equal to length times the width. And I will assume the length is twice the width, so L is equal to 2W times W will equal to 174. So from this one, W square will equal to 174 divided by 2, which is 87 meters square. And where is the W will be the square root of 87, which means how much?
9.32.
9.32, which is good. I can use 10. Sorry, I will use, I can say it's 10. So now find the L. So 174 is equal to 10 meter, L times 10 meter. So from this one, you can say L will equal to 70.4 meter. Use 18. Now, and why I am using like this, you will be when you have experience of this one. Usually, in the design try to have dimensions of not in point, or if you have in point, it should not be more than half. So L, now I will try to have 18 meter, and I will have W with 10 meters. So this is the time. Now, what about the time? What about the H? And I can say we have from the design parameters, also pathway, we have the horizontal velocity should be between 0.5 to 0.15. This is a horizontal velocity in the tank. Now you can assume this and find the H, or you can assume an H and find this one. Now I will try to use a horizontal velocity between 0.15 to 0.5, like this. Oh, sorry. Now assume horizontal velocity will be between 0.1 to 0.5 meter per second. I will assume VH as a point, let me say I will use 0.4 meter per second. Okay, so what will be the for velocity, or the horizontal velocity will, how can I take benefit from that? The velocity or horizontal velocity is equal to Q divided by cross-sectional area to this flow. This is the cross-sectional area. Now, dividing this one, so V horizontal, it assumes it will be 0.4 meter per second, which is equal to Q divided by area cross section. Then the flow is how much? It's 4,715 meter per day divided by cross-sectional area. What is the cross-sectional area for this one? It's the width times the h. And I have, sorry, this is h. So I have the w and I have the h. It will be equal to 4,715 meter cube per day again. And what is the value of W? I found that it's equal to 10 meter, and we need just the H, which is the unknown one, and this will be equal to 0.4 meter per second. And again, I should multiply this is day, sorry, per second. It's 24 hours times 60 times 60. So how much it will be? 0.4 will equal to 4,750 divided by 24 divided by 3,600 divided by 10. This is gonna be 5.49. And then convert it H. Yeah, this divided by 0.4. I think we made a mistake. 4,750 divided by 24 hours divided by 3,000. Okay, meter per second divided by 0.4. Okay. I think it's 1.3. Is that correct? I think it will be like this. Okay, or you can assume a value of h. The h will be between 2 to 6 meters. Usually we will use 3 meters or more. So use h equal to 3 meter and check for horizontal velocity. Now, if I have h equal to 3, so the horizontal velocity will become equal to 4,715 meters per day. And also this is day, this is 24 hours, 60 divided by the cross-sectional area. Now we have 3 times 10 meters squared. So what will be here? The value of V horizontal, the value of 4,750 divided by 24 divided by 3,700 divided by 13. Yeah, so the horizontal velocity, it will be 1.8 times 10 to the power minus 3 meter per second, which is very less than 0.1, not accepted. So we have to use another h. I think you get the idea, right? The idea is we have to assume a value for the h and check the values. Okay, we have to use check. And by the way, this is per minute, not per second. I'm sorry for this. We have to check with this one, please. 0.1 or 0.4 per meter per minute. Yeah, in our calculation, so it's 0.1 meter per minute. I have to check if this is minute. So 0.1 divided by 16. 0.1 divided by 16 will becomes 1.03, 1.6710 to the power minus 3 meter per second. Yeah, it's 1.8 times 10 to the power minus 3 meter per second. It's greater than this one. Okay, the design is okay. So the H can be used as 3 meter. Or in the previous calculation, we can, by the way, meter per minute, not second. So I will use 0.4 meter per minute. And when we are finding this one, okay, this is per minute, which means times 60, 1 minute is equal to 60 seconds. So it means the value here should be 4,750 divided by 24 divided by 3,600 divided by 10 divided by 0.4 and times 60. So here is H equal to 0.82 meter, or use H equal to 1 meter, which is not accepted. You have to use an H between 2 to 6. Is it the design procedure is clear to you? Barham, do you have
Yes.
any question?
No question, sir. Sir, should we know that we should choose a depth from 2 to 6 meters or a horizontal velocity from 0.15 meters to 0.5, or they'll be given in the exams?
These that are used for design. So these will be used for the design. So this is design consideration. When you are assuming a data, you have to check with a given. Now this is usually when you are an engineer, will be available for you. And also this design consideration between the L to W, and also will be given to you. You have to know that, but I'm not telling you to memorize anything, but you have to know that that one in your calculation. Besides of this one, you have the Q. When you are designing, for example, in our case, when we say that we have the length of the tank was, I think it was, the width was 10 meter, right? And the length was about 17.18 meter, right? So when we have the water is coming over flow of this tank, so the Q divided by, there should be a weir here. This is the weir. The weir means the place that is collecting water from the tank, clean water. Now should be checked. Usually the weir loading, it means it will be between 120 to 200 meter cube per meter there per day. Now we have 4,750 meter cube per day, and it should be divided by a number. The number is the whole length of the weir. This is the whole weir. Whole weir length. So in our case, we have 10 meter just from this side, and we have 18. Definitely, we will not take that 18 whole. We will take, for example, if I want to take 4 meter from this side and 4 meter from this side, so the total length of the weir, now it will be 10 plus 4 plus 4, which is 18. This is my design, 18 meter. I will check if it will be enough if I take only 4 meter from the hell and use it as a weir just for collecting the clean water or not. Now this is 18 meter. We have 4,750 divided by this 18. This is will be called as a weir loading. Now, what I have, the result will be 4,750 divided by 18. Now you can see it's about 263 meter cube per meter per day. It means every meter of this weir can be capable for holding 263 meter, which is a little bit greater than the allowable. So what we have to do, we have to release the load for the weir or increase the length. I will make it 5 meter by 5 meter. So now try 5 meter and 5 meter, and already we have this way 10 meter, so it will become 20. So 4,750 divided by 20, you can get it's 235 meter cube per meter per day. Now it can be okay. So final design will be look like this. The final design, if in case that you have to, the final design we have this way. Oh, sorry. The final design will be here. 10 meter from this way and 18 meter from this way. I think H was 2 meter, right? And there will be a weir loading. The weir is here, this weir. It will take 5 meter from this part and 10 meter from that part and 5 meter from this part. This is called the whole design or the design detail for this. Okay, look at the L to W here. So again, 4 to 1 to minimum 4 to 1. This is just for a design criteria, and this will be allowed for you. You may have them in the design, the question, by the way, and we'll give it to you as a table.